During the break today, Marvin Gaye may sing the national anthem. Okay. Where are we at? Ogden Hall, among other things. Okay. Where did we leave off at? Costa Lake, Neese Lake.
I think we're at the end of the
Can the sulfur be a leaving group? Why, yes, it can. Nucleophiles. Different ways to judge nucleophiles. Most of them are very similar to the same way you judge a base. You should look back at the acid-base handout. Rank each of the following according to nucleophilic strength from weakest to strongest. Probably should say strongest to weakest. Let's find the strongest. Which one's the strongest? I got some, okay, this is organic chemistry. Let's get rid of these spectator ions. This is minuses, okay? Well, I know an anion is usually stronger than a neutral, right? Okay? At this point, I can probably say, well, the weakest. Which one's the weakest? I think water is probably the weakest. So this is neutral. From weakest to strongest. Well, I reckon that's number one. Weakest. Let's go to the other end. What's the strongest? How about these two? Which is stronger? OH minus or SH minus?
SH.
Well, that was good. Why?
Bigger.
It's bigger. Why does that make it better? Further away, and why does that make it better?
The nucleus is holding on to the nitrogen, so
The oxygen holds them tighter. It doesn't let it get out there and do backside attack. That one's stronger than this one. Is that one stronger than that one? Well, that's another O minus. So probably, yeah. I think this is 4, being strongest, right? Weakest is 1, strongest is 4. Is that what we're doing? Okay, we have 2 oxygens. Let's draw them out. We got one that's hydroxide. What is other? OAC. What is AC? AC is acetyl. Altogether, it's acetate. An acetyl is a carbonyl with a methyl. This is an acetyl. This, with the O there, it is O-acetyl. And this O is minus. That's the anion of acetic acid. Okay, which is stronger? Nucleophile. Top or bottom? Why? Because this we know is delocalized. This is resonance delocalized. We can put the minus is really on that oxygen zone. Resonance. Resonance is going to make this a weaker nucleophile. So that's weaker than that. So this is 2, and this over here is 3. Is that right? Weakest is...
Yeah.
Yeah. That's weakest. This is next weakest. That's stronger than that because it's not resonance. That's stronger because the sulfur is a bad parent compared to oxygen.
If the question asks us to rank in terms of leading groups, would it have to be reversed? Before it have to be reversed?
Yeah, but these are all bad leaving groups. Unless you protonate of the oxygen. So you probably would not see that question. But typically, yeah, your leaving groups are typically like to be stable. I mean, which of these 4 is the most stable? Water. Water's the best leaving group. Yeah, because the hydroxide doesn't want to be a leaving group. You have to protonate it, and when it leaves as water. So yeah, it's kind of just the opposite. Okay, down here. Okay, all these are potassium salts. So F minus, CO minus, O minus, O minus, N minus. Which is the strongest?
N minus.
Cl.
N minus.
Well, let's just knock them off. Which is stronger, N minus or O minus?
N minus.
N minus because it's a bad parent compared to O because it's less electronegative. Doesn't hold electrons as tight. Okay? Fluorine, oxygen, nitrogen, then carbon. So that's stronger than these two. Is this stronger than F minus?
Yes.
Sure. Because F minus is a great parent. Holds those electrons tight. What about Cl minus?
Yes.
See, here we're not going straight across or straight down, we're going quarter diagonal. In the end, what does your intuition say? Which is more stable, Cl minus or N minus?
Cl minus.
Cl minus. That's why HCl is a strong acid. It likes to ionize and form Cl minus. Cl minus is pretty stable. See, chlorine is still electronegative. And it's more electronegative than nitrogen, if you look at the numbers. Typically, all your halogens are pretty electronegative. The most nucleophilic up here is this one. So, again, I wish we were going from
5.
so this is 5. Okay, what's the next? Really, your halogens are not that nucleophilic. See, we can start comparing apples to oranges here. Because if I throw you an I minus may be stronger than O minus because it's so big. So it's better when you're going straight across or straight down in the periodic table. Let's look at these two. Which is stronger? We got O methyl minus, or we have O tert-butyl. Well, the stronger one is going to be the oxygen that has the most electron density.
Methoxy.
What do we know about this in terms of its electronics? It donates. But over here, we got 3 branches, and they all donate sort of here. So which one is more electron rich? Yeah, this is more electron rich. Because we know true structure is more than just what we draw here. It's really got, electrons are being pushed towards it. More electron rich. See, here we have conflict. This is a stronger base.
That is not a strong nucleophile.
It's a stronger base. But not only is this more electron rich, what else can you describe about this? And it's a word that starts with an S-T-E-R. Sterics. Sterics is very important with nucleophiles. But sterically hindered. Okay? We have conflicting arguments here. It's a stronger base but weaker nucleophile. How do you rationalize that? Well, here's the first statement. When you do acid-base chemistry, sterics does not play a role. Because the H is so small, it doesn't matter that there's things blocking. And also there's a couple other reasons. In the end, take home is, when you do acid-base, sterics doesn't play a role. So all we would look at is electron rich. And the one on the right is the most electron rich, would be the most basic. But when things act as a nucleophile, what's the difference between a nucleophile and a base? Really not much other than this. When it attacks an H, it's called a base. When it attacks something else, like a carbon, it's called a nucleophile. But there is differences. That's why it has a different name. And one of the big differences is nucleophiles are subject to sterics. This is actually a better nucleophile.
Can you make a comparison with OH, or was this sterics too hard to determine?
That compared to hydroxide?
Compared to the the better one versus hydroxide?
It can get tough, because how big is the stairs? This is a little tough, and it requires some discussion, which is what we're doing. But in the end, I'm telling you that that's a better nucleophile. And tell me why that is. Because the other one is sterically hindered. Sterics is a big argument. So the next one is going to be this one. Then I would say that one. Because your O anions are still going to be better than these. These are your best parents. Halogens are good parents. Again, this could be difficult if I showed you an I minus. Okay? This series is a little bit tougher, but one of the reasons I give you this series is so we can discuss it. This should be clear. Which is the better nucleophile, F minus or Cl minus? Cl minus. So that makes this 2. Why is Cl minus a better nucleophile? Because it's a worse parent. It doesn't hold the electrons as tight. It's also bigger, which helps nucleophile. Because it's able to start bonding quicker as it approaches backside. Okay? Questions? Summing it up. What type of nucleophile can participate in an SN2 reaction? Here's your answer. I underline it. You might want to circle it and highlight it. And put a star beside it. Strong ones. Because of this reason. Which mechanism, SN1 or SN2, is the nucleophile involved in the rate determining step? SN2. Is it involved in SN1 rate determining step? No. The SN1 rate determining step is just ionization of the leaving group. Nucleophile has nothing to do. Because the nucleophile is involved in the rate determining step, it has to be strong and be able to do it. Strong. Okay? Which ones are strong? Here's my definition of strong. Anions, sp3 amines. Where have we seen that before? Strong bases. Anions, sp3 amines. There can be exceptions to this.
Would you put CH3 minus as stronger nucleophile than NH2 minus?
Yes. Because carbon is not as good a parent as nitrogen. Less electronegative. Strong ones. You will see exceptions to this, but when you see it, it's going to be a very difficult reaction. For example, is water a good nucleophile for SN2? Is it an anion? Is it an sp3 nitrogen? It's not strong. Is it a good nucleophile for SN2? No, it's not. Can you do a reaction with water SN2? You might can, but it's probably going to take very high heat and maybe a long reaction time. It's just not good. So this is not an absolute, but in general, you need a strong one. Okay, which compounds below are strong? Is this strong? No. Is that strong? How about this?
Yes.
Well, that's plus and this is minus, right? That's ionic. Okay? Forget about, is that strong? Yes. Is this strong?
Yes.
Yes, sp3 nitrogen. Is this strong?
No.
No. It's got a nitrogen, but that lone pair is conjugated in a p orbital. It's not going to be eager to do backside attack. It's busy doing resonance. Okay? KCN.
Yes.
Y'all remember KCN, the Sunshine Band? Back in the 70s? Okay, KCN. Well, this is plus, and that's cyanide, right? Is that a good nucleophile? Yeah, it's an anion. Water, no. There's also an exception to the anions. For example, CO minus, is that a good nucleophile?
Yeah.
According to my definition, yes, because it's an anion. But guess what? It's really not a great nucleophile because CO minus is pretty happy being CO minus. It doesn't want to go try to become neutral. So there's some exceptions to my general statement, but my general statement will get you going 90% of the time. Okay?
So of the halogens, you say only bromine and iodine are bromine and iodine?
Well, as the halogen gets bigger, it becomes a pretty good nucleophile. Because those electrons are just out there. Okay? Question here. Okay, let's look at various SN2 examples. Various examples. We're going to, all these should fall under what we've talked about before, but we're going to kind of give them names and look exactly what we're doing. First one we're going to do is alkylation of oxygen. We're going to put an alkyl group on oxygen. First one is going to be alkylation of carboxylic acids. Here's a carboxylic acid. We're going to put an alkyl group on this oxygen. And when we do, it's going to become an ester. How can we do that? First off, is this a good nucleophile for SN2? No, it's not an anion or a base. Now, is this going to be potentially the nucleophile or the electrophile for SN2?
Especially the nucleophile.
Well, the electrophile has the leaving group. Now, you might say, well, OH can be a leaving group, but it ain't going to leave that carbon because that carbon's not tetrahedral. Not in the mechanisms we know. In the end, this is going to be the nucleophile, but it's not a good nucleophile. How can we make that a good nucleophile? If we can deprotonate it and make the anion, then it would be good. So now it's an anion. How can we take the H off? Starts with a B. We want to use a base. Base takes H's, right? What's your favorite base?
HBr.
HBr is an acid.
Sodium.
Okay, we can use sodium hydroxide. What will that do to an acid? Well, okay, let's get rid of that. Hydroxide, right? These take the H, these stay behind. When they stay behind, what do you get? You get that plus water, and the sodium spectator sits with that. It's just an acid-base reaction. We can turn our neutral substrate into a good nucleophile by deprotonating it with a base. Now it's a good nucleophile. Now we can throw in a carbon with a leaving group, and now we can do an SN2. Now these electrons will come in and do the backside attack that partial positive, kick it off, all concerted. That looks like an SN2 mechanism, right? What does that give? Gives that bond right there. I like to highlight the bonds we just made. We just made an O-carbon bond by an SN2 substitution. Why is it substitution? Because there used to be a Br under my hand, but we replaced the Br with the nucleophile. That's an example of alkylation of a carboxylic acid to form an ester. Questions about that?
So that's what it's,
Browner?
so maybe it's more of a carboxylation of alkyl
Well, you can call it that too if you want. But it's certainly an alkylation of the carboxylic acid. And then that's more commonly to have this be the main substrate. Really either way. Usually whatever is your biggest compound, you call that sort of the starting material. And your smaller thing is more of the reagent. We could put the bromine here and put the carboxylate on the line. Either way. Alkylation of alcohols and phenols. And when you do this, it's called a Williamson ether synthesis. And typically in organic chemistry, you do need to know whenever you have a so-called named reaction, like Duhamel or Williamson ether, Friedel-Crafts, Michael addition. Whenever a reaction is named, it's a pretty important reaction. You need to know what that name means. Okay, first off, we're dealing with alcohols and phenols. Here's an alcohol. Is that a good nucleophile? No. We got to remove the proton, deprotonate it, make the anion, then it would be a good nucleophile. Well, sodium hydroxide, which happens to be the base that was suggested to be used over there, was a good suggestion. Will that deprotonate this? Obviously not. Why not? How do you judge acid-base reactions? pK of this is 16. What's the pK of the acid over here? What is the acid over here? Okay, water. That should have been an instantaneous answer right there. Okay, there's the H now. Water. What's the pK of water? 16. Which side's favored, 16 or 16? Neither side's favored. At equilibrium, it's going to be 50-50. So is sodium hydroxide strong enough? You've got to completely deprotonate this. Is that strong enough to completely deprotonate it? No, it only deprotonates half. And you may think, well, it's half good. Well, half is not good at all. You need to be protonating completely. Back up here, was sodium hydroxide strong enough? Well, yeah, we made that plus water. That's 16. What's the pK of a carboxylic acid? You gotta know pKa. 4. Okay? Which is favored, 4 or 16? 16. By how much? 10 to the 12. It's favored by 10 to the 12, which is what? About 100 gazillion. That's pretty much favored. See, sodium hydroxide is strong enough to deprotonate a carboxylic acid, but it's not strong enough to deprotonate a regular alcohol. Alcohol is not acidic because there's no resonance of the anion.
So what would happen if we protonated that oxygen, make it leaving group? That's not what we want, I guess.
No, we're using all of our these are all nucleophiles here. You could make that a leaving group, but then it would not be the nucleophile, it would be the electrophile. The thing with the leaving group is the electrophile. The electrophile gets attacked. To make anions of regular alcohols, there's 2 different ways. One is to use sodium metal. I'll put a 0 up there indicating the oxidation state of 0. Sodium metal. If you take an alcohol, react it with sodium metal, you'll get the, what do you want to call this guy? It's a sodium salt of the alcohol. What do you want to call this? That's an alcohol. 8 is not a bad ending, but more commonly, sodium plus, O minus. What is the minus ending? I, chloride, hydroxide. This is an alcohol. This is an al, it's spelled with a K, alkoxide. What does the alk mean? First off, let's look at this. It's an oxide, it's an oxygen anion. But the oxygen anion has what on it? An alkyl group, called an alkoxide. Deprotonation forms the alkoxide. Now that up there is called a carboxylate. See, the 8 ending is sometimes used. It's not called a carboxylide. It's called alkoxide. Most common way is to react them with sodium. You get the alkoxide plus hydrogen. That's the fate of the H. Now this is not a standard acid-base reaction. Okay? Because sodium doesn't have a lone pair. Sodium only has one electron. So you're not going to show a mechanism of the sodium taking the H. We don't form NaH anyway. This is actually a redox reaction. And most of your redox reactions, you don't show a mechanism with arrows because they're really radical reactions. And even then, they're not well described. But we can do a redox. For example, what's the oxidation state of a metal? 0. What's the oxidation state of the sodium now? +1. So the sodium has been oxidized. What's been reduced? Well, if you know how to do covalent oxidation states, the H here is +1. But now it's elemental hydrogen, and the oxidation state of elements is 0. So we went from +1 to 0, so the H has been reduced. So it's a redox. Now if you want to balance that, you're welcome to do it. You need 2 alcohols. Here we go. 2, 2, now it's balanced. 2 of these gives 2 of these and 1 of those. Okay.
You need 2 of those.
Hey, what?
Do you need 2 sodium solids?
Well, that's 2 means 2 of these, 2 of those. 2 of the complete set. As a side note here, if you take sodium and put it in like ethanol, it'll start bubbling. What are the bubbles? Hydrogen gas. Okay? But in the solution, or you can let it go dry, you'll have the alkoxide. So, that's the most common way to make the alkoxide. Once we make it, down here I'm just making it, okay? Here it is. Plus hydrogen, there's a sodium ion there too. But there's our main species. Once we make it, now we can throw in a carbon with a leaving group. And now we're off to the races. What can we do? Kick off the leaving group. The O can now become bonded to the CH2 with a phenyl, and we make that bond. What do we do overall? Oxygen has 1 alkyl group. Now it has 2. We've alkylated the oxygen and added another alkyl group. What's the name of this process? Williamson ether synthesis. Because the alcohol is now converted to a, see it's an ether? Whenever you add the extra alkyl group, it's now an ether. Let's look at phenols. Is sodium hydroxide strong enough to deprotonate a phenol? Phenols are more acidic than alcohols. 10. 16. Which side's favorite? 10 or 16? 16 by how much? 1,000,000. Okay? That's good. Typically you need a difference of about 2 pKa. Okay? So sodium hydroxide will work with phenols and carboxylic acids. Sodium hydroxides don't work with regular alcohols. So down here we can take phenol, react with sodium hydroxide, and get the sodium phenoxide. It's an oxide of a phenol called a phenoxide. I've actually seen it called a phenolate before, but the I ending is more common. Word of caution. Is the bonding between the O and the N covalent or ionic? Ionic, right? Everybody understand what the sodium bonds ionically? So why do I have the O right next to the Na? Right, I mean, that's just like writing NaCl. Does that mean they're covalent? What I'm trying to get at is, don't make this mistake. Don't do that. Because what does that mean? That's a covalent bond. No. That's just sort of like formula. And if I replace the Cl with an O, it's still formula, but the O needs to have something bonded to it. Maybe it has a benzene ring bonded to it. And that's what we got here. Okay? Once we make that, down here, we can make it. Now we can throw in a carbon with a leaving group. Oh, that's a great substrate. No sterics around the carbon, great leaving group. Let's get rid of that. I don't know why that keeps showing up. Bam! I mean, those H's are so small. That's just backside. There's no really, kick that off. And now the O is bonded to the methyl. We methylated our oxygen, we alkylated our oxygen. And lo and behold, the product is now no longer an alcohol or phenol, but a ether. So that's also a Williamson ether synthesis. Two-step process. Make your anion, then do your SN2. So that's alkylation of oxygen.
Whenever you have an ionic compound, right, is the Cl, is it going to have its traditional, I think this one,
Traditional what?
regular orbitals, s orbitals, p orbitals, and it's actually in that form, as opposed to some type of,
Could be hybridized.
they will still be hybridized? Yeah.
To tell you the truth, I don't know when an atom is ever going to state that you learned in. Maybe it is. Everything can be hybridized. Maybe a monoatomic atom, like sodium, maybe in that ground state you learned in Gen Chem. But chlorine is Cl2, so it's got to be hybridized to bond to the chlorine. Cl minus is an anion, I think it's probably still hybridized. Okay, making rings. If you take this compound here and treat it with sodium, you'll get this oxygen ring compound plus sodium bromide. What's going on here? Well, what is sodium going to do to this compound? I see an alcohol. What does sodium do to alcohols?
It's oxidized,
Deprotonate.
makes H2 gas.
Yeah, it essentially does deprotonate it. When I hear deprotonated, it sounds like it does the acid-base mechanism. It does. You could also say it leads to formation of the alkoxide. Sodium is going to get you this plus hydrogen. Okay, that's what sodium does to alcohols, right? Now once we have that, what can it do? There's a little partial plus over here. Bam. This is an internal reaction, known better as a intramolecular reaction. And with this oxygen bonds over here, what do we get? It's a ring with the oxygen 1, 2, and 4 carbons. It's like we made that bond. See, that carbon used to have a bromine on it, but instead the oxygen came around and kicked the bromine off, and now the oxygen is bonded there. So that's an example of a intramolecular Williamson ether synthesis.
way to predict the favorability of redox reaction? Simple way.
Didn't you do that in Gen Chem? I mean, don't you have like tables with potentials? Sodium reacts with alcohols completely to form the sodium alkoxide plus hydrogen. And this thing's going to just react. And the sodium ion will sit with the leaving group ion. What's below oxygen in the periodic table? Sulfur. Sulfur has very similar bonding and chemistry. It is a better nucleophile because it's not as good a parent. Any of the things we did with oxygen, you can do with sulfur. I mean, you could have a compound with an SH, you can react it with sodium or sodium hydroxide, depending on how acidic it is. Your body actually uses sulfur as a nucleophile a lot. And because it's better than oxygen, that's why your body likes to use sulfur. That's why some of your amino acids that contain sulfur are important, like methionine. So I'm not going to repeat up there. I'm just going to tell you a few little tidbits. Anybody ever heard of glutathione? It's actually sold at the drugstore in the supplement section. It's this tripeptide. Tripeptide meaning it's 3 amino acids bonding together. You get enough amino acids bonding together, you get a huge protein. But glutathione does a couple of different things in the body. One thing it does, it serves as a sacrificial nucleophile in the body. Because it has this here. And under certain conditions, this may actually be a minus. And of course, if it's a minus, it's an even better nucleophile. What do we mean by sacrificial nucleophile? Well, look at here. Methyl iodide. Very toxic stuff. Because nucleophiles, bam. There's no sterics. It's a great leaving group. And maybe your proteins have nucleophiles on them. And so you get this in the body, your proteins start reacting, and you get problems, toxicity, and maybe can lead to cancer or something. But see, your body has this guy. This is like Superman to the rescue. It's like, hold on, I'm coming, let me react. And you be protected. So it reacts, and you end up putting the methyl here, but because this is so polar and ionic in the body, it gets washed out of the body. So what did it do? It was a sacrificial nucleophile. I'm going to react instead of you. So your body uses glutathione for that purpose. Actually, Tylenol is toxic if you take too much. That's because if you take too much, well, what happens? Even one pill of Tylenol is potentially toxic. It forms a reactive intermediate that's bad for you. But your glutathione reacts and it's okay. It gets rid of that. But if you take too much, your body has a limited supply of this. And if you run out of that, then your proteins will start reacting. And particularly your proteins in your liver react with the Tylenol metabolite. And if you overdose on Tylenol, if you go to the hospital, what do they give you? Mucomist. They give you overdose on Tylenol. Why? Because Tylenol is going to form this toxic metabolite. They don't want your liver proteins reacting. They're like, let's give the patient this and let this react. Understanding chemistry allows you to understand other things and go on and do great things. Okay, oxygen, sulfur. What about amines? Let's look at direct alkylation of amines. Now with amines, there's no need to make the anion first. Why? Because an amine, if it's sp3, is a good nucleophile in the neutral state. Let's actually look at, as an example, back on the very front, what's going on right here. We've already looked at it once. Here we have sp3 nitrogen. Which atom is most nucleophilic in this molecule? Nitrogen. Otherwise, it'd have to be an anion, and I don't see any anions. So here's your nucleophile. You put this in, you got a carbon with this mesylate leaving group. Could be a bromine or an iodine. This attacks here, kicks it off. You're doing SN2, and now the nitrogen is bonded there. Now I said this before, that nitrogen has an H. So when it bonds, it has a plus charge. You have to include a base to get rid of the H. That's why they include the carbonate. Okay? So this is your potassium carbonate. This acts as a base, takes the H, leaves these electrons behind, and that's how you get your neutral amines with the lone pair again. This is an example of a direct alkylation of an amine. Difference is, you don't have to remove the H first. Instead, you remove it afterwards. And at this point, it's pretty acidic, and just about any base can do that.
So is the 2 carbons on the mesylate group and then the 1 or 2 hydrogens and 1 on the nitrogen basically make it so it doesn't have steric hindrance, or like is it not a better word? It seems like there's a lot going on both of these.
There's a little bit of steric hindrance, yeah. Apparently it works. But yeah, it's always good to question steric hindrance. That's not a tertiary amine, so it's not as bad as it could be. What type of carbon are we attacking? Primary, secondary, tertiary? It's primary carbon, so that's not sterically hindered at all, huh? Not secondary. If it was tertiary, we certainly would not be attacking tertiary by SN2. So that's an example of what we're talking about. Direct alkylation. It says, see, section F4, is that what it says? Where's F4? There's FF, there's G. Oh, yeah. We saw one before earlier. When we were looking at leaving groups, we were focusing on that SAM, and the sulfur was the leaving group. And we did this. That attacked the carbon and kicked off the positive sulfur. We're focusing on the leaving group, the sulfur leaving. But what's the nucleophile? A neutral amine. It's a good nucleophile. Now the nitrogen's bonded to the methyl. But where'd the other H go? So it has to be lost, because when it first bonds, I mean, it's positive with 2 methyl, 2 H's, and 2 alkyls. Something has to take the H. Well, in the body, there's all, I mean, even just water can take this, or some type of base. Sometimes you see base just kind of drawn generically. I really hate this. You really need to know what base you're dealing with if you really need to know it. Leave these behind. But something has to take the H to go neutral. Everybody see that? So that was an example of, that nitrogen has one alkyl. How many now on the nitrogen? 2. So we added an alkyl, with methyl being the alkyl. So there's another example of direct alkylation of nitrogen. On the very back is, I think, is either Zyrtec or Allegra. We'll look at that, but on the very back of this handout is another one. Let's look at some potential problems with this. Here's a potential problem. If you try to react this with ammonia, carbon with a leaving group, it's a good electrophile for SN2. Ammonia is a good nucleophile. We can attack here, kick that off. What does that give? It gives this directly before we lose the H. Now you may think that's it. You just treat it with base, it takes the H, and you get the neutral amine. Just like we did here. Problem is, it doesn't just stop here. It has very good potential to do other things. For example, ammonia can act as a base. And there's ammonia here. If ammonia took the H, we would make the neutral plus ammonium. Now that can do that. And if we remake this, well, then that's a nucleophile, and it can react again. If it reacts again, we get another alpha or nitrogen, and this is shown neutral. And instead of adding just one alkyl, like maybe you wanted, you end up with 2. Well, guess what? This can now react again. It can keep reacting, and what you may end up with, instead of this, you may end up with a nitrogen with 3 alkyls on it. Because it equilibrates, and this becomes nucleophilic again. That's a potential problem with direct alkylation. Now, does it always happen? No, they did it on that synthesis of Allegra. This is potential. Because of this, there's lots of indirect routes to getting an alkyl on a nitrogen. One of the indirect routes is making this compound, which we just showed, and making it the other route. It's a problem. Making it this way. React this with sodium, what is N3 called? Azide. Sodium azide. You all have it in your car, hopefully. Where is it at in your car? It's in the airbag, right? And whenever something initiates, the azide explodes and inflates the airbag, right? Probably learned that in Gen Chem. I didn't learn azide in Gen Chem? Okay. Well, azide's a common anion. What's the charge of azide?
-1.
-1. How do you know that? Because sodium is +1. Yeah. N3 minus. Okay? Lewis structure. Didn't I ask you the Lewis structure of that on test 1 in the workbook? I thought there was azide in the workbook. There was. Page 3 in the workbook. I'll do that. It had an H on it. There was an H here, and so it was HN3. Yeah. Well, without the H, it becomes, if you take the H off, it becomes an anion. Okay? But the same Lewis structure was there. Okay? So, it's a minus. Now, if you draw out the Lewis structure, it's actually double bonded like this. How many total electrons? Nitrogen is 15? No. How many nitrogen? 5, right? 5 times 3 is 15. But it's an anion, so that means it's got an extra one. 16. There you go, there's 16. And every atom has an octet. Charges, this is minus, and that's plus. Actually, all three are charged. What's the net charge of that beast? -1. Okay? One of these nitrogens, your choice, acts as a nucleophile, kicks it off, and what do we get? Well, that nitrogen is now bonded to there. So we have N, minus on the N, plus there. This nitrogen is now bonded to an ethyl. We just made that bond. And now the whole thing has what charge? Neutral. It's an ethyl with an N3. See, that's it there. Ethyl with an N3. There's a lone pair there and 2 here. The other lone pair is now bonding to the carbon. Well, here we go. This is an alkyl azide. By the way, those are very, they cause allergic reactions. Azides. You gotta be careful with azides. Not only are they explosive, and we can use them in airbags and stuff. They're also, as at Georgia State, somebody was working with azides, and they had a reaction, like a skin reaction, had to go to the hospital. Okay, but this, if you react with H2, we're not going to do mechanism here, but it will cleave this by reduction. It'll put H's on everything. And if you put H's on this and cleave it, what do you get? You get that. I'm not going to show you the end product of the other two. Actually, I don't know what it is. I don't know if it's nitrogen or if it's like hydrazine. In the end, you can reduce azides with hydrogen and a metal catalyst to the amine. And this is an indirect route because we didn't react the nitrogen just directly with the there, like on the previous page. Direct route would be like to take ammonia and try to make that. There's many other indirect routes, and in organic 2 we see a few other ways to make alkyls. That's what I say here. Let's look at quats, and then I think we'll take a short break. Many of you have encountered quats. What's a quat? Well, it's short for quaternary. What does quaternary mean to you? It's an atom with 4 carbons to it. Well, here we have a nitrogen with 4 carbons. Nitrogen with 4 carbons, but because nitrogen don't make 4 bonds usually, it's a plus charge. Okay? It's called a quaternary amine salt. It's going to have a minus with it. Very often just called a quat. Many of you have used quats. You have it in your purse, something. Zach, you got quaternary in your purse? Yeah. Maybe not you, but where is it at? If you go to the Y, they have like a container of it sitting on the post, and you put your hand under it and do your hand like this. Antimicrobial. Yeah. A lot of your quaternary ammonium salts are antimicrobials. Look at your thing. They're usually either plain ethanol, but I know the one, the Y, I looked at it one time, it says something, quaternary ammonium bromide or something. Okay, how do you make quats? SN2. We start with this tertiary amine, does have a lone pair. It may be a little sterically hindered, these groups around it, but it still will react. Maybe it would need heat to react because of the sterics. But if these electrons add here and kick that off, what do you get? Well, you get this. It's now bonded to that. But see, this nitrogen can't go neutral by losing an H, like we did in the other ones. And so that's just the end product. And you could remove all the solvent, and it would probably be solid because it's ionic. And then you could dissolve it in something and put it in a container and call it an antimicrobial agent. Apparently, the ionic nature disrupts the cell wall of the bacteria. I don't know, I have never taken biology. Some of you guys take biology? How does that kill the bacteria? There's different mechanisms. Somehow it... here's a big old quat. With a big old name. It's called didecyl. What is a decyl? 10 carbons. Didecyl dimethyl ammonium chloride. Yeah, that's the one I saw at the Y. I think that's when I wrote it down on the handout. Next time you're over there, check it out. Or wherever you go to the gym. What is this one over here? It's called choline. Choline you'll see in biochemistry. But guess what? The nitrogen is a quat here. And if you make an acetyl over here on this oxygen, it's called acetylcholine. Or most commonly called, instead of saying acetylcholine, it's called acetylcholine. Acetylcholine has the quat nitrogen there. Okay, that's what a quat is. So what have we done? We've used oxygen as a nucleophile, sulfur, nitrogen. What else could be a nucleophile? What about a carbon? What if you just have this here? Can that carbon be a nucleophile? Well, there's an H there. I don't see a lone pair. How's it going to act as a nucleophile? To be a nucleophile in SN2, the atom has to have what? A what? A lone pair. That's the thing that adds, right? If you don't, look back here. I showed the nucleophile and I specifically showed a little dot there. Okay. Carbon doesn't have a lone pair. So, we'll figure out how to get it a lone pair. Let's take a 3 or 4 minute break.
One or two. Yeah, we're gonna hire.
I didn't say that.
Okay, guys.
Got 4 years for him. Careful.
I got, like, it's actually 13 years of classes and more time. I just think that, I just explain. How was that?
Let's get started. Questions about anything we went over? Huh?
Good.
Why don't we just call it a day?
Well, if you like, I mean, test is on Wednesday. I mean, if you think you want to just cover it on your own, we can just, I'm fine with just showing up on Wednesday. But hopefully you learn from the lecture, get your questions answered, generate new questions. Any questions been generated today? Okay, alkylation of carbanions. Carbon can't be a nucleophile if it doesn't have a lone pair. With a lone pair, it's going to be a carbanion, we call it. Okay? No lone pair here. Can we remove an H and leave a lone pair behind somewhere? That is there an H that's acidic? Yeah. At the end of test 2 material, we talked about alkyne H's being really acidic, or acidic enough to do chemistry with. What base did we use to deprotonate an alkyne H?
Lithium use.
We used N-butyl lithium, which is a carbanion, lithium plus, or we used NaNH2 minus. Both of these are strong enough to take the H and leave the lone pair behind, and that gives the carbanion. And so this is why we need to know that alkyne H's have some acidity. pKa is about 25, listed in the table in the back of the workbook. But now that we have the carbanion, now we have a good nucleophile. Has a long pair, has anion, good nucleophile. Now we can throw in a carbon with a leaving group maybe benzyl chloride. And what can happen? These electrons can add to the carbon, kick off the leaving group. And what does that give? So draw the product there, and once you draw it, highlight the bond that was made. So we get that right there. The alkyne carbon is now bonded to the benzyl carbon instead of the chlorine. And we generate CO minus. So now we're back to having to generate the anion, like we did in the Weaves and ether synthesis. And the alkyne anions are often called acetylide anions, acetylene being the simplest alkyne. That was at the very bottom of the last handout before test 2. Where else do we see carbanions? We've already seen this today. KCN. That's K plus CN minus, but the CN is a carbanion. What is DMSO? That's dimethyl sulfoxide. That's a common solvent. Very polar. Since I call it a solvent, that means it's inert. It's not going to do anything. Show the product of this reaction. Looks like you got a little stereochemistry at the beginning, huh? What stereochemical outcome do you expect? Got the product drawn? product right there. Question, comment?
Why can you not draw the CN coming in from behind going away?
No, how's the CN coming in, Rudy?
I guess, like to the left.
The CN comes from right here. On the plane of the board. Bromine is that way, CN comes in this way.
Looking at that plane, can I push the hydrogen? Okay, it's fine.
Questions about that one?
Was there a trick that you did to get that automatically flipped the right way? Because the CN came from the other side of the funnel, and now you have the CN listed on the bottom, just
What's the mechanism here?
that side.
SN2.
SN2? How do you know it's SN2?
Because this section's under SN2.
Because we're doing SN2s right now? Okay. How do you know it's SN2 though?
Good leaving group and good.
How do you know it's SN2? Because you got to know the mechanism, because SN2 gives inversion, but SN1 gives racemization.
Strong.
It's good nucleophile, good leaving.
What type of nucleophile do we have? Strong. Strong nucleophile is going to be what? Let's go back. I don't know if we stated this. We said what type was required for SN2. Maybe we'll say this later, or maybe we're going to say it right now. To do an SN2, you need a strong nucleophile. But you can also say this. If your nucleophile is strong, it's going to do SN2. Because strong nucleophiles are bullies. They can't keep their nose out of things. They're like, here I come, backside attack. I want to be involved in the rate determining stuff. I'm strong. Okay? Strong nucleophile is going to be bimolecular, SN2. Note that I said bimolecular. Which one is bimolecular, SN1 or SN2? Yeah. And when we get to elimination and do E1 or E2, which one of those is bimolecular? E2. See, there's two bimoleculars. If it's strong, it's going to be bimolecular. That's not it. So we know it's SN2, so the stereochemical outcome is what? Inversion. Okay? This is 1, 2, 3, H to the back R, so the product's going to be what? S. That's S. That's S. You can draw it either way you want. That's the same compound. You agree that R is going to get S when we do inversion? No?
Because you have a different group added to it, correct? Or will it always be something that wouldn't change the priority?
Okay. You're exactly right. There's a potential where it would not. For example, if the nucleophile was H, you could change priority. Yeah. Yeah.
Just leave it.
But when it's CN, which is the high priority group of the three? It's still CN. You see, you still, the new group is still high priority 1, and so you still get the same outcome. R becomes S. You're exactly right. But 99% of the time, you're going to go from R to S or S to R when you do inversion. Okay? Now, why did I draw it both ways? Because if you want to draw it the true inversion, the CN comes in over here, right? When it comes in, it kicks off the BR. So there's the carbon. The CN is now going to be over here. Okay? Here this is. The CN comes in, it makes these rings go flat, and when the bromine leaves, what do these groups do? They then come this way. And so instead of that, this is now just going to come this way a little bit, but it's still going to be bold. The phenol's going to come this way a little bit. Now it's like a 180-degree bond angle, so I'm going to draw it more like this. But this is the one on the right, just turned a tweak bit. So I showed it both ways. That's why I showed it both ways. But they're both S. Do it however you want. Just make sure if this is R and you get inversion, you show S. You got to know we're doing SN2. How do you know we're doing SN2? Because we're using a strong nucleophiles. Strong nucleophiles are bullies. I'm not waiting on you to ionize. I'm coming in backside. On the other hand, let's look at this example. We take this carbon with the leaving group and heat it in ethanol. We get all these products up here, HBr just being the byproduct. So we're moving on from carbanions. What's the mechanism here? First off, is it substitution or elimination? We haven't done elimination yet. What's going on here? Looks like the Br is being substituted with the ethanol, and it loses an H. Same thing over here. The Br is gone, the ethanol is there. Both are substitution products. Difference is, looks like here, this replaced the Br on the carbon, but how did that get over there? That's interesting. Substitution, you know, two substitution mechanisms, SN1 and SN2. What's the mechanism? I hear SN1. Anybody else? Cosio? SN1 or SN2? Why do you say SN1? I would look at the nucleophiles. The nucleophiles strong or weak? Nucleophiles, ethanol, strong or weak? Aaron? Weak. Okay, so what's the mechanism? We stated earlier to do an SN2 it has to be strong. So it ain't SN2. SN1, right? Okay? Now that it's SN1, what's the first step? Let's do mechanism. What's the first step? That just has to ionize. And what do we get? Carbocation. You see, the ethanol is weak. It's not going to come in there and do a backside attack. It's too lazy. It won't get off the sofa. All that can happen is just the leaving group ionizing. But now we're doing unimolecular chemistry, okay? Carbocation chemistry. How do you get the first product? What attacks there? Now we got the ethanol. Interesting. Now I'm not strong enough to attack a partial positive, but I don't like a full positive. I'll get off the sofa now. But we're doing an SN1 mechanism now. What does that get? Oxygen with an ethyl, but there's an H here. We haven't lost that. There's only one lone pair. That's a plus charge. Now how do we get the first product? We just have to lose the H. What can take it? Well, the leaving group can take it, leave these behind, and we get that product right there, plus the HBr. And that's a good old-fashioned SN1, right? Which one's the rate determining step? Formation of the cation. That lazy guy is not involved in the rate determining steps. Too lazy, too weak. This is fast. And that's fast compared to the slow rate determining step. How do you get the other product over there? What are cations known to do? Rearrange. There's an H here. What do we need to do to get... Looks like cation must have been there. How can we get cation there? These electrons break away. And when those electrons do that, what does that give? You have cation there, a new H here. Now the ethanol could also end up attacking here. And I'm not going to repeat, it's the same thing, but you can end up with that. Which one do you want to call favored, the first one or the second? Well, based on our carbocat, what we said with alkenes, if you can rearrange, always do that. That was secondary, this was tertiary. We're going to say it would probably rearrange. And so we're going to say this is the major product. What about stereochemistry? Major product. Do we have to be concerned with stereochemistry? No, there's no chiral carbon. The carbon with the oxygen is not chiral. What about over here? Well, that's chiral. I'm not telling you what it is, so you can't deal with it. Here, though, what type of outcome we're going to have there? That is, how does the ethanol attack there?
Either side.
Either side, right? So this here is going to be, we know that's going to be racemic, because when you attack a cation, you attack them either side. I don't know what this over here is, I didn't tell you. Whatever you started with, it's over there, I don't know. But the major product, there's no chiral carbons at all, so there's nothing to consider. It's like a paper clip. There's only one way to make a paper clip. There's no right or left. So now we're moving on to SN1. And do you see how that looks like an SN1? Weak nucleophile, carbocation, prone to rearranging. That's a classical SN1. Questions about SN1? Let's go down here. That's stereochemistry down here. Label these up here as A and B, so we can refer to those. It's the same reaction down here. If we say A plus B, with B being major, there's no stereochemistry with B, so you just draw it like that. What would the A product look like? We pretty much did this above, but just draw what the A product will look like. We're going to have bromine here, but is it going to be dashed, not bromine, we're going to have the O-ethyl there. Is it going to be dashed or bold? I would draw it like this and then indicate racemic. Now you could draw both. And if you drew both, what's the relationship between the two? Not enantiomers. You're going to be diastereomers. Okay? You're going to be diastereomers in this case. Everybody understand why they're going to be diastereomers?
But for B, is it be bolded and dashed? Or is it
No, B is going to be right there.
But are we using the bolded and dashed?
What do you want to bold and dash? Well, there's nothing chiral. Is there a chiral carbon? No, so it doesn't matter. Yes, that's tetrahedral and one H is forward and one H is back. You don't need to show that. Yes, that's tetrahedral. One of these groups is forward, one's back. But your choice, whatever you like to do. There's only one possible arrangement. Since there's only one possible arrangement, you don't really need to show it. But it is tetrahedral.
Does the heat have anything to do with predicting the intermediate that would form, or is it only in the final product? And since here we don't really do it, make a difference in the final product.
The heat is to probably help it ionize. This is called a solvolysis reaction. Why? Well, typically when we say something is a solvent, we say it doesn't react. This is a case where you probably just dissolve this in ethanol and heat it up. And obviously the ethanol reacted. So it's like this is both solvent and reactant. And when your solvent does react, you often call it a solvolysis reaction. Solvent comes, what does lysis mean to you? Lysis means, cleave. We broke the carbon-bromine bond using the solvent, sort of. That's what it means. So that's just terminology, where the solvent actually is reacting here. What is the rate equation for the above solvolysis reaction? For forming either product, what's the rate equation? Rate equals what? Some type of constant? Times what?
Just the one on the left, just the bromine.
Concentration of the alkyl bromide? Because it's SN1. Is the ethanol involved in the rate limiting step? No. What type of nucleophiles react strictly by SN1? Weak. Weak. Got a weak nucleophile, you're doing SN1. Weak nucleophile, too lazy to do SN2. Because to do SN2, we're asking that nucleophile to come in backside, attack a less reactive carbon that's only partial positive. Summing it all up. Here we go. Substrates with leaving groups on primary only SN2. Why? Because you'd never make a primary carbocation. Substrates with leaving group on tertiary only SN1. Why? Because a tertiary carbon is too sterically hindered from backside attack. Substrates with leaving groups on secondary can undergo either. How would you tell? It could be tougher, but maybe you've shown the products and the product has inversion. If the product has inversion, the mechanism must have been SN2, right? But if your products have racemization, where it became racemic, the mechanism must have been SN1. You also have rate information. What if you don't know which mechanism you're dealing with? How could you use rate? Actually, this question is asked on the back. We'll come back to this. Turn to the very back. Here we're making Zyrtec, another antihistamine. We've got this reaction right here. Product shown over here. It's actually two steps. The second step, well, the first step is they're reacting this here. I'm not going to show mechanism because we don't know it, but the nitrogen ends up bonded here. You see, there's that carbon. It used to have a bromine, now it's a nitrogen. In the second step, they take off this ester group. Let's don't worry about that. But in the first step, they include a base. Why? Because eventually you got to remove the H. But then afterwards. 10 hours. Heating 10 hours seems like a pretty slow reaction. Why do you think it's slow? Well, a little bit of sterics. It's secondary. Now, if that was tertiary, you wouldn't do it at all if it was SN2. Question. Well, I say it's SN2 most likely. And if it's SN2, it would involve this attacking here and kicking that off. Is this a good enough nucleophile for SN2? Yeah, it's just sp3 nitrogen. It's just good nucleophile. But I say most likely. That means I'm not sure. How do I confirm that it's SN2?
Increase Atkins concentration, see the speed of the reaction.
How would I use rate equation to tell if it's SN2? Josh? What is the rate equation if it's SN2? It's a constant times what? Concentration of the nucleophile times concentration of octobromide, the electrophile. Yeah, it's the concentration of both. Okay? If it's SN1, what's the rate equation? It's only some constant times what? Times the electrophile, the leaving group. So if it's SN1, is the nucleophile concentration relevant? No. What I can do here is I can do the reaction, determine the rate, that can be done. I can then maybe double this concentration and repeat the reaction. If I double this and the rate doubles, which mechanism am I dealing with? SN2. But what if I double it and the rate doesn't change? Sounds like probably SN1. Now, if I had some stereochemistry, I could use that outcome, but see, there's no stereochemistry here. Actually, there is. I mean, that's Carl. They're not showing stereochemistry up here. If that was R, I would expect S here. So I could use that, but, right? That's another way you could judge it. I think it's SN2, well, you should be getting inversion. If you end up with racemization, your mechanism is probably SN1. Okay, so that's a couple of there. Let's go back to summing it up. With strong nucleophiles, the reaction will always be bimolecular. Now, we haven't covered elimination yet, but SN2 is bimolecular substitution. This is bimolecular elimination.
So if you have a strong nucleophile, but the leaving group is a tertiary carbon, is that a reaction, or you can undergo SN?
No. If it's a strong nucleophile, it will always, I would underline always, bimolecular. So I mean, it's not SN1. But since you can't do SN2, it's probably E2. So we haven't got to E yet. Or maybe it won't react at all, but no. Okay, with weak nucleophiles, which are lazy, reaction will be unimolecular. As long as the substrate is secondary or tertiary. If the substrate's primary, you don't want to form a carbocation in there, the reaction will have to be bimolecular. So bimolecular reaction with weak nucleophile will be quite difficult. At this point, we're getting into a reaction might not happen. Certainly going to be difficult. Okay. On the last page here is just show products. And what mechanism? Does it have stereochemistry? Depending on the mechanism, stereochemistry. Let's do the first one here. I'll leave some of these for you to do on your own. Then we'll look below where we sort of maybe supply a reagent. All right? If you heat this in water, still we're doing substitution. If you heat this in water, do you envision SN1 or SN2? SN1. Why?
Not strong.
What do you? Because we have a weak nucleophile. And as we just said, if your nucleophile is weak, it's going to be unimolecular. SN1. Now that it's SN1, show the problem, including the stereochemistry. You think mechanistically? First step is going to be ionization. Something in attack, what's going to attack? Yeah. You might consider a rearrangement. Is that possible here? It's going to be that, it's going to be racemic. Plus what? What else is going to be formed here if we balance it? HBr. Racemic means I can draw it two different ways. You've got the OH bold or the OH dashed. It's both R and S. Because we have a carbocation intermediate. What if we do the same reaction with the, instead of using water, KOH? Now our nucleophile is strong. And we said that when it's strong, it's going to be bimolecular, so it's going to be SN2. So let's show the SN2 problem. Now we have a strong nucleophile.
So, for that first one, whenever the BR leaves, you will have a resin stabilized carbocation. It makes a good carbocation, but a weak electrophile, or weaker than the regular plus.
Yeah, it'll be weaker than normal.
Oh, we don't worry about
It's
the
delocalized, but it still will react. Over here, we're going to have this here looks like it's S, and that's going to be R. There you will get inversion because your mechanism is backside attack. Concerted, kick it off. No carbocation over there. SN2. I'll let you do this one on your own. How about this one over here?
Elimination.
What's the mechanism?
Is it final? Elimination.
SN1.
E2.
Reaction.
Tertiary.
E2.
Nucleophile, strong or weak? So is it going to be SN1 or SN2? Okay. Halides on a tertiary carbon. You can't do SN2 on a tertiary carbon. Let's go back. Strong nucleophile means it's going to be bimolecular. But you can't do SN2, so what's the only option? SN1 is not bimolecular. This is going to be E2, and that one takes us into elimination. Okay? That reaction is going to be E2. Strong means bimolecular, but you can't do SN2 because the leaving group's on tertiary. Didn't we say we couldn't do that? That's good. That's a classical setup to do E2. This over here looks like, I'll let you do that. Let's look below. You may be asked to supply reagents. How would you convert this to that? There's actually two different ways to do it, depending on which bond you want to make. You could either make the O-methyl bond, or you could replace all this with a new O-methyl. Two different ways. Think about it. Think about both ways. Down below, okay? That one requires a little bit more thinking. This is pretty straightforward. Go back and look what we did today. You can get even bigger molecules. That's, anybody know clindamycin, Cleocin? Usually if you have like a procedure done in the hospital, they'll give you some Cleocin as a prophylactic antibiotic. IV. Anybody in the nursing field or anything? You know Cleocin? Okay. There's Cleocin. This is lincomycin. That's clindamycin. Because this has a chlorine here where it used to be OH. Can we replace an OH with a chlorine? No. How can we make that a good leaving group? Protonated, and then the nucleophile would be chlorine. Okay. Lincomycin was first isolated from some microbes in the soil. Microbes produce it. It's amazing that a bacteria can produce molecules like this. You know? It used to be used as antibiotic, but they found if you replace that with chlorine, clindamycin is actually a better antibiotic. By the way, this was isolated in some soil in Nebraska. They grow corn, but they also grow good microbes. But let me ask you a trick question. What city in Nebraska?
Lincoln.
Yeah, Lincoln, Nebraska. That's where it was discovered. Huh? It's amazing, right? It's all in the name, right? Usually names supply you some information. Okay, that was free information. That's SN1, SN2. Questions? Let's look at the elimination handout so you can get started on that over the weekend. Actually, I'm just going to say, look at it on your own, okay? Please be looking at it ready, because what I want to do is, these few minutes left, we did not go back and... Let's look at the mass spec handout real quick. This page here, were you able to assign compound to each spectrum? Somebody have one assigned? By the way, when we finish up here, the info session is 11 o'clock, right over in Science Hall. So we'll make it over there. There'll be a sign-in sheet.
What room was it?
Same room we had IR in.
1002.
Well, maybe we were in a different room. 1050. Anybody have these assigned? The last one you said was the first spectrum. Okay, this is what you need to do for each one. Hopefully you've done this. What did you predict for cleavage here, Brianna? You just did what?
I just like calculate the motion.
Well, they're all 88.
Yeah, and then I just, yeah.
And they all have an 88 T. So how did you assign this to the first one?
I like, was I put it on?
Okay, for each one you got to predict. What do you predict for this one, right? What do you predict for this one? This one. What numbers do you predict?
57.
You predicted what?
You can click on the method group. Just copy the image.
No, I mean, what did you predict? Laura? Lauren? No? No. Melissa? What did you predict? To give what mass? To be what? Okay, I'm not seeing that anybody's predicted anything. Barbara, what did you predict?
It would lose the methyl.
Lose a methyl to make what? To make this? Okay, that's a nice tertiary, well, it's resin stabilized. That's loss of what? M minus what?
15.
So 88 minus 15 is 73? So you predicted a 73? Okay. Well, which, I see a 73 there, I see 73 here. I think the one below doesn't have a 73.
That'd be major, I mean, the best.
Okay, but what else was predicted here? Okay, we'll try again on Monday. Hopefully we'll get it done by Wednesday when test time comes around. Okay? Again, how do you do mass spec? You predict your cleavages, and then you look at what you got.